All right, let's just dive right in. The world, when you really think about it, is just built on connections. I mean, everything from our social circles to the very molecules that make up our bodies. And for the very first time, AI is actually learning to see and understand this hidden architecture. So today, we're going to explore this totally fascinating field of graph representation learning. Just think about it for a second. Your social network on your phone, or how scientists are able to discover new life-saving drugs, or even how your favorite streaming service just seems to know exactly what you want to watch next. It's kind of spooky, right? So, what is the hidden thread here? What's tying all of these seemingly random things together? Well, it all comes down to a really simple but incredibly powerful idea: the graph. As you can see, a graph is just a collection of objects, we call those nodes, connected by a set of interactions, which we call edges. So think of people in a social network as the nodes, and their friendships, those are the edges connecting them. It's a surprisingly simple way to map out pretty much any kind of relationship. Okay, so you have a graph. Now what? How do you even begin to make sense of all those connections? Well, the most intuitive first step, the one we'd all probably take, is to just start counting things. And the most basic thing to count is a node's degree, which is, literally just the number of connections it has. You can think of it like a simple popularity contest. Who's got the most friends? Who's the most connected person in the room? And check this out. This is a brilliant example of how powerful that simple count can be. This is a network of political marriages between powerful families in Florence. And guess what? One family had way more connections than anyone else: the Medici. Their high node degree was a huge signal of their influence, and it kind of predicted their rise to dominate the whole political landscape. But, life isn't just a popularity contest. Is counting up direct connections really enough? What about the quality of those connections, or the overall shape and structure of the whole network? To really see the full picture, we've got to go deeper. And this brings us to the next level, and it's a really, really big idea: embeddings. What if, instead of just counting, we could create an actual map of all the relationships in the network? So the question really becomes, how can we capture the geometry of a network? Not just who's connected to who, but who's close, who's far away, who's part of a dense little clique, and who's acting as a bridge between totally different groups. The answer is something called a node embedding. And here's the best way to think about it. An embedding gives every single node a coordinate, kind of like a GPS location, but on a map of relationships. On this map, nodes that have similar jobs or similar neighbors in the original graph are going to be placed really close to each other. As the source material puts it so well, the goal is to project nodes into a latent space, where geometric relations correspond to relationships in the original graph. So in other words, we're basically turning this complex web of connections into a geometric map. And that is the breakthrough, because that's a format a computer can actually understand and use to make predictions. So how does a machine learn to draw this map? Well, it uses something called an encoder-decoder framework. The encoder's job is to take each node and give it a coordinate on the map. Then the decoder's job is to look at that map and try to guess what the original connections were. If the decoder can successfully rebuild a whole network just from the map, then we know we've created a really good, really meaningful map. But we can take this one giant leap further. I mean, that map of relationships is super powerful, but it's kind of static, right? What if the nodes on that map could learn from their neighbors dynamically? What if they could actually talk to each other? And this is the core idea behind what's currently the state of the art in this whole field: graph neural networks, or GNNs for short. So at the very heart of a GNN is this process called neural message passing. The best way to think about it is like the nodes are having a conversation with their direct neighbors. They're exchanging these messages, which are really just vectors of numbers, and they use what they hear to update their own understanding of their place in the network. It's so cool. This conversation happens in rounds. In each round, every node first gathers up, or aggregates, the messages from all its immediate neighbors. Then it updates its own embedding, its coordinate on that map, based on that collective message. And then the process just repeats. With every round, information travels one step further out, so a node's embedding gets richer and richer, pulling in knowledge from more and more of the graph. Okay, so we've gone from just counting connections to creating maps to having the nodes on those maps hold entire conversations with each other. Why does any of this matter? Why does this journey from these abstract ideas to these complex models actually matter in the real world?
Because it is powering some absolutely incredible breakthroughs. I'm talking about chemical synthesis, where GNNs treat molecules like graphs to help design new drugs. They're completely changing 3D vision, they're building smarter recommender systems, improving complex question answering AI, and helping us analyze massive social networks. It's all about understanding those connections. So let's just quickly recap our journey up this ladder of abstraction. We started with the basics, node statistics, which was kind of like a popularity contest. Then we moved up to node embeddings, which gave us a sort of GPS for relationships. And finally, we got to graph neural networks, which let us have a dynamic, network-wide conversation. Each step gives us a much richer, much more powerful way to understand the hidden structure in our data. What we're really seeing here is the beginning of machines that can see the world not just as a bunch of isolated data points, but as a rich tapestry of relationships. And that leaves us with this one final fascinating question. As this technology gets even better, what new hidden connections are we going to uncover about our world, our biology, and maybe even about ourselves?